This is multivariable calculus, and in this video, I'm going to talk about sections 15.1 and 15.2. 15.1 is where we start to understand the idea of a double integral, and then in 15.2, we're going to start to talk about just some of the basic mechanics of solving a double integral using antiderivatives. So we're really shifting in terms of our focus here. So we have been focusing on partial derivatives and applications of partial derivatives. And now we're going to move on and start to get into the idea of double integrals and eventually triple integrals as well. So like I mentioned when we were dealing with partial derivatives, a lot of the stuff that we do in multivariable calculus is directly tied to the things that we did in two-dimensional calculus. So when we were dealing with partial derivatives, a lot of the setups were the same. A lot of the mechanics of solving a problem were the same. And the same thing's going to apply when we deal with multiple integrals. So double integrals, triple integrals. So that's really what we're going to look at here is the idea of a double integral. And if you remember back to when we first talked about integration, back in, whether it was calculus AB or BC, the first time you saw integration. So the first thing we looked at was the idea of a definite integral. And when we looked at definite integrals, we talked about investigating them using rectangular approximation. So we would add up rectangles to approximate the area under the curve. Well, now we're going to be looking at things in 3 dimensions. So if I am talking about a double integral, which is essentially what we do when we're working in 3 dimensions, when I start looking at what's underneath my function, I'm no longer going to get an area, I'm going to get a volume. And you can see in this picture, if I'm thinking of the function z and I'm integrating that function z, what I'm going to get is all of the volume between the function z and that region that I've got it defined here, the region R. That would be essentially that volume would represent the value of that double integral. So the process for solving these is a lot like what we did before in the sense that when we're going to approximate these, instead of breaking things into rectangles, we're going to break them into 3-dimensional versions of rectangles, and we're going to use rectangular prisms. So you'll see that when we start setting these up and solving them out, it'll look a lot like what we were doing before. So the main thing here is we've got a region defined, and you can see this is the notation we're typically going to use for a region. So AB by CD, that's going to go in the same order as your variables. So A to B is basically going to be the domain on the x-axis, and then C to D is going to be the domain on the y-axis. Okay, so we essentially have that domain given there. Okay, so when we are looking at this and we're trying to find these double integrals, we want to think of them in terms of volumes. And when we think of them in terms of volumes and we think about approximating them, we're going to break these into, instead of having that large region, we're going to have smaller subregions. So you can see on this first diagram here, I've got that same graph that we were looking at a minute ago, and now you can see that region R has been broken into a bunch of smaller regions. And what I'm going to do then is I'm going to approximate a rectangular prism over each one of those regions to approximate that volume that is contained between my function and the xy plane. Okay, so eventually we're going to have a bunch of those prisms and we're going to add them all together, and that's going to give us a volumetric approximation. And just like when we did integration in 2D, when we were using rectangles, eventually we took the limit as the number of rectangles approached infinity, and that gave us the exact area between the curve and the x-axis. Well, then now what we're going to do here is we're going to take the limit as the number of these subregions approaches infinity, and that's going to give us the exact volume between our surface and typically the xy plane. Okay, so when we do these approximations, because this is really our main focus in this section, remember before we would do left-hand, right-hand, or midpoint approximation. Well, so that was pretty well defined. We only had really 3 easy ways that we could reference the function values when we were looking at that type of a setup. But when we're working with these subregions, I can take a sample point anywhere within one of these smaller regions. And so within any of these subregions or subrectangles, it doesn't really matter where these points are. When I'm trying to do in approximation, I'm usually going to consistently choose points to be in some certain location within the region. But the idea is I can really choose them anywhere within the region as long as I start making those subregions or subrectangles small enough, then eventually the value of my approximation is going to approach the value of the actual volume that is contained. Okay, so here they're just kind of taking random sample points to find the height of each one of those rectangular prisms. And like I said, we're not usually going to do it that way. We're usually going to have something that's defined, like when we did a left-hand, right-hand, or midpoint approximation, it would be defined for every one of them. But here it's just kind of showing you that it doesn't matter where I choose them, as long as I start to make those subrectangles approach an area of 0, then eventually what's going to happen here is I'm going to get the value of the integral. So here's what we're doing is we're adding up. You can see here, we're essentially adding up all of those regions. So I've got the function defined at each of those sample points. The x with the star there and the y with the star, those are essentially saying the function at our sample points. And then the delta A is just the area of that subrectangle. So I'm going to add all those up. That's going to approximate my volume. Now here what we're doing is we're taking the limit as the size of those subrectangles approaches 0, because we're going to take an infinite number of subrectangles. So we're essentially saying in the x direction and in the y direction, we're going to make those distances get infinitely small. And now that just becomes our double integral notation. So just before, when we would take the limit as n approaches infinity, and we were looking at a summation representing the sum of all the rectangles. Now we're looking at a limit as the two dimensions approach, or the two dimensions in the x and the y direction approaching 0, or the number of subrectangles approaching infinity. We're going to take that limit, and that's going to allow us then to get the exact volume between the surface and typically our xy plane. So you can see this is the integral notation, which is essentially the shorthand notation. Now notice the double integral notation has underneath it, we've got the region R, and sometimes we'll write in the limits of integration. Sometimes we can just say the region R and then define the region R separately. But that's the notation that we're going to use. Okay, so like I said before, what we're going to do is we're going to go through and we're going to approximate these in this first section. And then in the second section, I'm going to start to show you how to evaluate double integrals. We're just going to do it over rectangular regions for today. But eventually we'll get to regions that are defined by any curves. Okay, so this is the main idea. That's your integral notation. Okay, so now let's talk about how do we actually approximate these. So it's not really difficult to do, but you are thinking three-dimensionally as opposed to two-dimensionally. So it requires, a little bit of thought outside of what we were doing with rectangles. You have to kind of visualize these things because you can't just draw it on your paper. You've got to be able to kind of be able to think about how things are going to look, or you're going to have to graph them maybe in GeoGebra 3D and take a look at the surface and then visualize what those rectangular prisms would look like. Okay, so let's take a look at this first example. It says estimate the volume of the solid that lies above the square, and it's this region 0, 2 by 0, 2. So that means we're going from 0 to 2 on the x-axis, 0 to 2 on the y-axis, and below the elliptic paraboloid z equals 16 minus x squared minus 2y squared. So you can see the surface has been plotted there, and it says divide R, the region R, into 4 equal squares and choose the sample point to be the upper right corner of each square. Okay, so notice they told us where to choose our sample points. We looked at that diagram a minute ago, and they had kind of random sample points all over the place. And as long as I'm making these subrectangles get infinitely small, it doesn't matter. Well, when I'm doing an approximation, I want to be consistent with where I choose those sample points to be. So here they told us to choose the upper right corner of each square. So I'm going to go ahead and mark those off here so that I'm consistent with where I evaluate these. So the upper right corner of each square, I'm essentially looking at those 4 points. Okay, so I've got those drawn in there kind of as a reminder that this is where I need to evaluate these sample points. Okay, so now we're going to approximate this volume. So for my volume, the way I approximate it with these regions is I go through and I'm thinking about this first region that goes from 0 to 1 on the x and 0 to 1 on the y. I'm going to evaluate my function at the point 1, 1, which obviously we would plug 1, 1 into that given function, 16 minus x squared minus 2y squared. And then the area of that square is just an area of 1. So that would be the volume of my first rectangular prism. Then I'm just going to go to the next one. I'm going to go and look at my function at the point 1, 2. So I'm essentially looking at that region right now. Okay, so when I do that, again, I'm going to evaluate the function at that point, which means I'm going to plug into 16 minus x squared minus 2y squared, and then I'm going to multiply by the area of this region, which again, it's a square, that's 1 by 1. Okay, so then let's move on to the second piece here. We've got the function evaluated at 2, 1, and area of that square is going to be 1. And then the last region, this region where it says 2, 2, that means we're going to evaluate our function at the point 2, 2. We've got an area of that region of 1. And if you were to plug in, I'm not going to go through all of the evaluation here, but if you were to plug in all those points into your function, add up all the values essentially, since we're multiplying by 1, you would get an approximate volume of 34. Okay, so it's not that difficult to do. One thing I do want you to notice is the way that they referenced these regions. R11, R12, R21, R22. So those are corresponding to the points. There's different ways you can reference these, but that way if I want to reference one of those rectangular prisms, I can say, oh, it's the rectangular prism R12. Now I know that corresponds to the one using the fact that we're using upper right corners. I know that that is the region that is at the point 1, 2. Okay, so like I said before, really the idea behind this is just an approximation. And eventually what we would want to do is we would want to start making those subrectangles or those subregions get smaller and smaller and smaller. And that's what we're showing here. As we increase the number of subrectangles or subregions, the error in our calculation is going to get smaller and smaller and smaller. So you can see on the next one, we've got here, instead of using 4, now we've gone to 16. So we essentially doubled in both directions the number of regions that we're using. So now we've got 16 subrectangles or subregions, and that gives us 16 rectangular prisms. And then we double it again in terms of the size in the x direction or the y direction. And so you can see we're getting more and more accurate. And so really what we want to do in the end is we want to take the limit as the number of those subrectangles approaches infinity, and that's going to give us the exact volume. So like I said before, in this section, really what we're going to do is just approximate. In the next section, we'll start actually evaluating some of these. All right, let's look at the next thing here. So if we are going to do an approximation method, and we're going to use, instead of like a predefined upper right corner or upper left corner of each region, we can also do what we call a midpoint approximation. The midpoint approximation, though, has to be the center point for your subrectangle. So typically the subrectangles are going to be defined by squares, but if they're not squares, then you've got to find the actual center point for that rectangle. So you just find, obviously the center X point, the center Y, and that's going to give you the center point in that region. And that's really all they're talking about here if you're going to do the midpoint rule. Okay, so pretty simple to do. It's basic geometry and basic calculations with the overriding idea that conceptually we want to be focused on what these things represent and don't get caught up in just the computation, because the computation is very, very simple to do. Okay, so one other thing we can look at is the idea of an average function value. And again, I'm going to go back to 2D to help explain how this works in 3D. So remember when we did average function value with integration back in two-dimensional calculus, we would find all of the area underneath our curve, and then we would divide by the length of the interval, and that would give us sort of an average height for our rectangles, and that would give us the average function value. So we're going to do the same thing here, except for when we do this in 3 dimensions, when we find the integral, we're finding a volume. So if I want the average function value, that's an average, z value typically, I'm going to have to divide by the area so that what I'm left with is just the height of the function, which is or the height of the rectangular prism that would represent the volume. So when I divide by that area, it gives me that average height or the average function value. Okay, so essentially here, this should look very familiar if you remember average function value. So this is what I'm going to use when I do average function value in 3 dimensions. I'm going to find the double integral of that region. So that's going to give me the volume, and then I'm going to divide by the area of the region, and what's left is going to be the average function value, or the average, z value, if you want to think of it in XYZ terms. So very, very easy to do. Now, right now, we haven't really talked about actually solving a double integral yet, but we can still do an average function value using our approximation methods as well, which is what we're going to do in this section. So here's an example. It says, find the average value of f of xy equals y sine xy over the rectangle 0, 1 by 0 pi over 2 using 4 equal squares with sample point at the upper right corner of each square. So we're doing upper right corner again. Now I'm going to draw my subregion here. You might want to do this at first and maybe even all the time when you have to do these approximations, because it makes it a lot easier to remember where your points are supposed to be. So this is my rectangle, and I don't have this scaled perfectly, but the main idea is when I go in the y direction, since I'm using 4 here, I'm just going to break this apart, and I went from 0 to pi over 2, and then in the x direction we're going from 0 to 1, so this would be at 1/2, and this would be at 1. So we're supposed to be using the upper right corner of each square, so just like we did the last time. And again, they can define these points to be anywhere. They told us to use the upper right corner. So those are the four points that we need to be looking at. Okay, so when I do this, if I want to find my average value, okay, so I know I'm going to divide by the area of that region. So the area of that region I have in the x direction a length of 1, in the y direction pi over 2. So I'm going to divide by pi over 2, because that's essentially dividing by the area of that rectangle. Now, for the double integral, I can't actually solve a double integral yet, right? We haven't talked about that yet. So what we're going to do here is we're going to use 4 equal squares, and we're going to get the 4 rectangular prisms to approximate what that integral would be. So instead of writing an integral here, I'm going to put in my 4 squares. Well, each one of these squares, if I look at the function value, I'm going to evaluate at the upper right-hand corner. But if I look at what is the area of each one of those squares, because that's going to be my base, and then the function value is going to be the height, I could actually factor out the area of each square since they're all the same. And that's what I'm going to do here. So the area of each square is essentially 1/2 times pi over 4. So that would give me pi over 8. Okay, so that's the base area for each rectangular prism. And now I'm going to multiply by the sum of all of my sample function points. So f at 1/2 pi over 4, that would be that first subrectangle. We're going to do plus f at 1/2 pi over 2, and so on until we get through all of these. So let me see if I can fit these on this line. I might have to go to one more line here. So f at, let's see, 1 pi over 4. And then the last one would be f at 1 pi over 2. So we would have to actually go through and evaluate those. You could just do that on the calculator. And so what we'll do then is plug these into the calculator, which is a little bit tedious, right? Because we don't have a multivariable calculator. So that means you're going to have to plug in the points individually and then plug that into the calculator to evaluate. So it takes a little bit of time, but in the end, you should get a value here of approximately 0.884. Okay, so that's what we should be looking at on that region from 0, 1 to 0 pi over 2 if we were to get the average function value. Okay, so it's still the same general concept as 2D, expanded now into 3D. All right, so let's move on here. We do have some simple properties that are introduced in this section. You'll notice these properties look exactly the same as the properties that you knew in two-dimensional calculus. So this is now expanding to 3D. If I have a constant multiplied by my function, I can factor the constant out of the double integral. If I have a double integral of a sum or a difference, I can break it apart into separate integrals. Sometimes that's useful when we have to use different integration techniques for the different parts. And then the last thing is, if we have a double integral over a region, we can break that region into two pieces. Or if we have a double integral over two regions that have an intersection, we can combine those into a single integral. Okay, so now let's move on to 15.2. And this is where we're really going to get into the idea of just the mechanics of solving what we call an iterated integral. Primarily, we're going to look at double integrals over rectangular regions. But when we talk about iterated integrals, it just means we're going to do more than one integration. Okay, so fairly simple process, but like I said, our main focus here is primarily just the mechanics, but I still want you to be thinking about what does this actually represent. Okay, so I gave you a couple of integrals here, just where we're only integrating with respect to a single variable, just to get this clear in your mind that when we do these double integrals, we can integrate with respect to either variable. And it's just like when we did partial derivatives, right? We would essentially treat the other variable as a constant. When we took the derivative, when we did a partial derivative with respect to x, we would treat y as a constant. Or when we took the partial derivative with respect to y, we would treat x as a constant. Same thing happens when you do the antiderivatives. So for example, on this first integral, it's the integral from 0 to 1 of xy squared dx. Well, if I were to solve that out, my antiderivative would be x squared y squared over 2, because the y squared didn't change, but the x, I added 1 to the exponent divided by the new exponent, and now I would evaluate that from 0 to 1, and I would just end up with y squared over 2. Okay, now I can do the same thing if I integrate with respect to y. If I do that, this antiderivative would be xy cubed over 3, and I can evaluate that from 0 to 1. And now remember, when I plug this in, I'm plugging in for the y. That would give me x over 3. Okay, so that's kind of the main idea. Now, when we do this in a double integral setting, we just have to keep straight in our minds which antiderivative we're doing. So here is an example. We are doing a double integral over a rectangular region. And my y region, notice that we've got dy and then dx. We always work from the inside out. So we're going to integrate with respect to y first. That means that these are y values. So the y region goes from 2 to 4, and then we're going to do the x next. That means this is my x region. So I have a rectangular region that goes from 1, 3 in the x direction to 2, 4 in the y direction. Okay, so let's work through this. So when we do the inside integral, we're still going to have the integral from 1 to 3, but now we're going to take the antiderivative of this expression with respect to y. And that's going to give me 40y minus xy squared. Okay, so we've got to evaluate that from 2 to 4. And then we're still going to have to integrate with respect to x when we're done. Okay, so we would have to go through here and plug everything in. Remember, we're still going to use this outside integral later on. But when I plug in my 4 and my 2, I'm going to get 160 minus 16x when I plug the 4 in. And I'm going to get, let's see, now I'm going to plug the 2 in. That's going to give me minus 80 minus 4x. And this is all going to end up getting integrated then with respect to x. Okay, now I'm doing a lot of intermediate steps here. You may end up skipping some of these steps when you get really good at this, but just to make it really clear what's happening here, I'm going to show everything. So if I combine everything now, I've got 80 minus 12x. And now I've simplified this down to where I've just got now an integral of a single variable, and this becomes really, really simple at this point. I'm not even going to work through those steps. You know how to do that, and that would give you 112. Okay, so the main idea is you work from the inside out, and you have to be really careful about which variable are you currently working with, because you've got to keep straight in your mind what those limits of integration are referring to. Are they referring to x values? Are they referring to y values? Okay, so now here's the same problem. Notice the limits of integration have been switched. So when we solve this out, let's just go through the process here. And I'm going to skip some of the steps this time, but the main thing here is notice that we've got dx, and we've got those same limits of integration from 1 to 3, and then dy is now on the outside. So that means we're going to integrate with respect to x first. And when I do that, inside of this, when I integrate with respect to x, I'm going to end up with 40x minus x squared y. That would all be evaluated from 1 to 3. And what you can also do if you want a reminder is you can actually write x equals 1 to 3. If you want to remind yourself, what am I plugging in for? I don't typically do that, but it is a good way that you can keep in your mind straight what actually is happening. You could also just look at the fact that the second variable there is dy, or the second differential expression is dy, and that would remind me, okay, I just did something in terms of x. But you do have to kind of keep that straight in your mind. Okay, so now at this point, I've got an integral from 2 to 4. When I plug in and I simplify everything down, I'm going to end up with 80 minus 8y. And now I just essentially have an integral in terms of a single variable. And it actually turns out, when I solve it, I get the exact same solution. So when we do double integrals over rectangular regions, it doesn't matter what order of integration we use. You can see here we got the exact same result. And that's actually what this theorem says. This is Fubini's theorem, and it's just essentially saying what we just did, that the order of integration doesn't matter when we're doing a double integral over a rectangular region. So we can do it in whichever order. Sometimes it's easier in one order than another in terms of the antiderivatives, but really there's not really going to be a significant difference in terms of what's required to solve one of these, whether you choose to do x first or y first. Okay, so let's take a look at the second part of this. So the second question. So it says, use a double integral to find the volume of the solid that is bounded above the plane z equals 4 minus x minus y and below by the rectangle. And it's this region 0, 1 by 0, 2. Okay, so you can see we've got the region drawn over there. Remember in the last section, we were looking at rectangular prisms to approximate volumes like this. Now we're actually going to be able to find these volumes. Okay, so pretty simple to do here. And again, the order of integration doesn't matter. But if I want to do my volume here, I'm just going to put the x on the outside, but I could just as easily put the x on the inside. But in the end here, the function is 4 minus x minus y. And I chose to do the dy integral first and then the dx. So that would be my setup. Now, when I start solving this out, and again, you might start to be able to skip some of these steps algebraically if you're really good with combining some of these things in your head, but I would caution you on that because it's very easy to make mistakes if you try to skip too many steps here. But when I go through the process, I'm not going to show you every single thing here, but I'll show you the main steps. The antiderivative here with respect to y, I'm going to get 4y minus xy minus y squared over 2. We're going to evaluate that from 0 to 2. And remember, that's y equals 0 to y equals 2. And then dx. And now, when I end up solving that out, I'm going to end up with an integral that goes from 0 to 1. And I'll be left with 6 minus 2x. And when I solve that out, I end up with a value of 5. So that volume that I'm seeing there, the volume of that region would be 5 units. Okay, so now there's one more here that I want you to try. And it says evaluate this double integral. And we've got it over this region R, and it's y squared x dA over this rectangle. So the rectangle is -3, 2 in the x direction, 0 to 1 in the y direction. So I want you to solve it, and then I want you to think about what does your solution actually mean. So pause the video, Solve that out. When you come back, I'll show you the solution. Okay, so here is what you should have ended up with. And you can see we got a value in the end of -5.6. It doesn't matter if you integrated with respect to y or x first. It makes no difference. But the main thing is we got a negative this time. So remember when we would take an integral in 2D and we got a negative? That meant there was more area below the x-axis than above the y-axis. Same general idea here, right? If we're going to find an integral and we're thinking of it in terms of volumes, volume that lies below the xy plane gets treated as a negative. Volume that's above the xy plane gets treated as a positive. So this is essentially telling me that there is more volume below the xy plane than there is above the xy plane. So when I see a negative, that's really what that is representing. So keep that kind of straight in your mind. Again, you don't want to just blindly solve these things out and not have any reference to what's actually going on geometrically, because in the end, we're going to be doing problem solving with this stuff, and we want to be able to really have a firm grasp of what is happening with all of this volume in relation to our function and what does it actually represent. So try to keep that in mind as you work through the problems. It's very easy to sort of treat this as a simple algorithmic process, but really try as best you can to keep in your mind on every single problem to either visualize what this volume is going to look like, or actually graph it on maybe GeoGebra 3D and take a look at the region that we're actually describing here. Okay, so that's all I have for you in this section, and we're going to expand on this as we go through this unit. So you really have to have this process down. Doing these double integrals over rectangles, super, super easy, but you will see that this is going to get much more difficult as we start to change the way the regions are defined, and then eventually we're going to work our way into triple integrals. So you've got to have a really strong foundation in this and get really used to the idea of solving these out. So make sure you practice with this and really pay attention to those details.